morning. Welcome. We have been looking at the discretization of the steady 2D diffusion equation. And I just want to ask you to correct two typos that I noted after we had already done yesterday. That is, if you saw more, just please tell me. That was on the right-hand side, like that, of equation 39. And the right-hand side then was having, say, the phi at the boundary that was given. That was the first branch. And then we had the phi at 2, at 1, 3.1. And then we had the boundary condition at phi a2, and then I had here written a the phi 1, 2 to the phi n I2, but these are the unknowns that we want to determine. And the phi b2, that is the boundary condition. So that should be, so there were two typos, so the stuff in the beginning, then, so the phi a2 is the boundary condition, that is correct, but then it is not the, we have the right-hand side, and the right-hand side was denoted by D. So it was D, 1, 2, and it is all the D's, and the last one here, it is a D, Ni 2, and the boundary condition is phi b2. So the boundary data must come in here. So that was, so this phi here, that was wrong. Okay?
Excuse me, is that 0 or A? B?
This is A.
Okay.
That is the boundary condition. So that was all correct. It was just that instead of phi, I had a D. So then we have straightened out that. And then we have I've already mentioned that the system of which we only saw the upper left half, but which will continue, as I told you, as we continue to write down the equations, that corresponds to a block tridiagonal system. So that is the so 39, that is the one that we started to derive. If we could continue with that, that corresponds to a block tridiagonal system. And as I said, this is linear if the diffusion coefficient does not depend on the unknown. And even if it is, we have to iterate, and then the matrix is in each iteration linear anyway. But what we will get in the end is something that you already see in this part from the lecture notes, that is the very end of the lecture notes, of chapter 11, and that is, we have here then the unity matrix, and then we have here block matrices, which I denote A1, B1, A1, and C1, and that were the matrices we looked at yesterday. So, and this pattern that will continue all the way down until we get to B, and that is then nj, because we go across the I lines, and then we have there, and then we do that for each j, we go across the I direction, and then we get from the first cell line to the last one, this is nj, and then we have in the center the matrix A nj, and we have the C nj. So we have these matrices, and in the end we have here a matrix, a block matrix, which is, I call it nj plus 1. And so that is, and every else here we have just 0. And the unknowns, and the way we did it, we took then the boundary into account, and now the phi that I write now, they will be vectors. I explain them in a minute. So the phi 1 will then also a vector. That will be our unknowns for the whole line, I line, in the first cells next to the southern boundary. And then we continue to that. Then we get to our unknowns in the row adjacent to the upper boundary, which is then nj. And then we have the boundary conditions at the upper boundary, which are then denoted by phi nj plus 1. And then the right-hand side is then consisting of our unknowns. The d0 are the boundary conditions at the bottom, and the d1, that is for the boundary conditions for the first row, and the d2 is the one that we have concentrated on there. And here we have then the dnj and the boundary conditions at the upper boundary, dj plus 1. So, and now in here, so that is our system, and you see we can write it if we want as a matrix A. So this, we write it in this way. This is the matrix A. It's a block paradigm matrix. And here is our vector of unknowns, phi, and here we have the right-hand side, D. Now we want to see what these elements are. In this matrix, the A0, that is the nj plus 1, they are the identity matrix. And you shall see quickly what the dimension is. The d0, that is now the right-hand side here. Let's see, if we take that first, let's see, the d0, that is equal to, and now we take in here the boundary conditions. We take the boundary conditions from the bottom. And that was denoted by 0c, that is at the left boundary. And that should be the same as the boundary condition that we have at the left boundary, and that is then A0. So A0. So phi A0. That is the same as phi 0c. And then the next ones are phi 1c, and so on. The next but last is the NIC, and the last one is at the right boundary, that is the phi NI plus 1c, and that should be the same as the boundary at the right, which is the phi that is denoted by B0. So that is the boundary conditions at the bottom. And the, let's see, if we take that directly, let's see, if we take the boundary conditions from that were the boundary conditions at the lower, so at the lower boundary, and we can also take the boundary conditions at the upper boundary, that is the D nj plus 1. And then we have it's a similar, we have the boundary condition now at y equal to yd, it's upper boundary, and that should be the same as the left boundary, which is the phi, and that is at a, and we have here the nj plus 1. And then we just continue the way down, phi 1d, and so on, to phi nid, and the last one is then ni plus 1d, and that is then in the upper right corner, and that should be the same then as the phi b at nj plus 1. So these are then giving us the boundary conditions. And the phi j that is most interesting, that are our unknowns. Phi j, they are then containing the boundary conditions. So that is then the phi 0j, that is now on one line, that is at the left boundary, and the phi 1j, and so on, the phi nij, and the last one is at the right boundary, ni plus 1j. So then we have the phi's. Let's see, what else do we need? I think we have that. And now we can focus on the matrices. We have looked yesterday at these three matrices, and the ones that we have here, they will just be similar. So the Bj is a diagonal matrix. I make life now a little easier by writing as a diagonal, and in the diagonal we have 0, and then we have the f coefficients, which are coming from the minus as. That is then 1j and so on up to f nij 0. So that is a diagonal matrix, and likewise the C is a diagonal matrix. So the C, capital Cj, is a diagonal matrix that contains then the corresponding G coefficients, which come from minus a north. So that is then the G1j until to the Gnij, and the last one is a 0. And the A coefficients, the A matrices, AJ matrices, they are tridiagonal matrices which start with a 1 in the first row, and in the second they look just like the ones that we had already in 1b, and that we have now just to add the index j. So it's index 1j, 1, j, and we have the index a1, j, and c1, j. And these are from the AP coefficients. These are from the minus AW, and these are from the minus AE coefficients. So, and that continues all the way down, and it is just as in 1D, and the last ones are, next but last ones are Ni, j, the A and I, j, and the C and I, j. And the coefficient is 1 in the last row. So, and the rest is just 0. So, let me see if I got everything. I hope so. And you see now what the dimension of these matrices is. Here you see it clearly. We have here ni plus 2. That is because we have the plus 2 because we have taken the boundary conditions into account. So all the matrices that we have here are ni plus 2 by ni plus 2 matrices. And they form then this block triagonal matrix. Everywhere also these I are of this dimension. So then we have this structure here, and if we look at it, then we see that it corresponds, as I said already yesterday, also to a pentadiagonal linear system. Because if you imagine this is in the A's, the A1 to ANJ. So they have all something in the diagonal and something next to the diagonal. And the B and C, they are a little further away. There are some zeros in between. So, but in the end, it is 5 diagonals, and that is then a pentadiagonal matrix. So then we can say that the block tridiagonal system that we have here, that is our system 4T, that can also be viewed as a pentadiagonal system. Pentadiagonal system, because it has 5, that is penta in Greek, diagonals. Okay, so then we have established that. And then we have completed the discretization of the steady 2D diffusion equation by the finite volume method. So what we see here, we end up with a block tridiagonal system corresponding to a pentadiagonal system that we have to solve to get our unknowns. You see, the unknowns that we get are for each phi 0, we have n I plus 1 unknowns. And altogether, you see here, we have nj plus 2. So nj plus 2 times ni plus 2 unknowns, because we have taken the boundaries also into the unknowns. Okay, so then we have to solve that, and that is then the step number 3. We have now done step number 2, the discretization, and after we have defined the grid, and now done the discretization, we now solve this system of equations. So that is in step 3, and that is solution of the system of equations and that was the system that we had seen derived A phi equal to D. And that we are discussing in the chapter that we start directly, that is in chapter 12. There we shall discuss that. I have a couple of remarks, because what we have been doing is we have been looking at the finite volume method in 2D for rectangular control volumes. You can imagine that the generalization to 3D is straightforward. We have just to add the fluxes over the ends that we neglected. So we get also then fluxes from there, and we will not get unknowns of the order ni times nj, but ni times nj times nk, because we have also then a number of grid points in the third direction. So we get larger problems, but the principle is the same. We get a matrix that has 7 diagonals. That's a heptadiagonal matrix. And so it just adds some more work. But the principle stays the same. The extensions to structured grids is also very simple, because we can take advantage of the structure. We don't have then that the faces are delta x times delta y or something, but we have then the face area. we have to consider that. But the discretization gets very simple because the d phi dn we can just do by the neighboring cells. So we can take the values in the neighboring cells, divide by the distance, and we can do that for any polygon. In fact, that makes it also easy to generalize to unstructured grids. For unstructured grids, however, we need a data structure that supports our method. That is a phase-based data structure. But otherwise, it can be done, and it is done. Because most of the CFD tools rely on the finite volume method. But we want instead start now chapter 12 to see how to solve the system that we derive. And that is then, we start that now directly. That is the solution. And we restrict ourselves here directly to linear systems. Because, as I said, even if we had a nonlinear problem, we linearize, and then for one iteration it gets a linear problem. For systems of equations. So the problem that we consider here is the one of the following kind, and we shall use now this notation. It is different to the notation that we have been using, but this is the notation used in linear algebra. So AX equal to B. The A is a given real, and we take it here also different notation, n by n matrix. So n is now our dimension. For the problem that we were considering before, the little n would be ni plus 2 times nj plus 2, the number of unknowns. That is given, and what is also given, that is a given real L vector. And the solution is x. So x solution is to be determined. And that is supposed then, hopefully, an n vector. So, n vector x is to be determined. So that is our task. So we have converted our problem of solving a partial differential equation, in that case for steady state, for diffusion problems, to a problem of linear algebra. And we have now two options. One option is the one that you learned in linear algebra using a direct method. That can be done, and we have been doing that now for exercise 8, and you have seen the advantage of doing it. So we have direct methods. And the example that we have been studying also in exercise 8 now is the Thomas algorithm. So that means, and this matrix that we get there is a tridiagonal matrix. So let's see, the tridiagonal linear system that we get for the 1D finite volume method is an example of a banded system. And the more general expression for that is also sparse matrix. But banded is saying more, because the A matrix that we get in 1D has the following structure. It has a diagonal, and it has two diagonals, one above and one below. And the rest is just 0. So, and then that is, and you see the name, it has these bands, it's the diagonals. They are the diagonals. And this matrix actually has bandwidth 1. And you can count that here by the number of elements that are not 0. So here we have here a 1, and we have also here a 1. So we have one diagonal off that is not 0, of the diagonal. We have a definition for that, for the bandwidth. And those of you who took TP4280, Introduction to CFD, have already seen that. Matrix A is said to have bandwidth W. If the following is true, if the element in the matrix Aij is equal to 0, whenever the absolute value between the indices I minus j is greater than w. So when in that case, when the difference of an index, for example, here we have A13, the next one that is 0, the difference is 2, larger than 1, that is 0. So you can test that for everything, so you see that it will then work. And for this matrix, you have seen now in exercise 8, the TDMA is really beautiful. So instead of doing a bunch of unnecessary iterations, you solve it directly. And what we needed there was that A is diagonally dominant, therefore you are checking that. Diagonally dominant. And if you look in the papers, then it would also need another prerequisite, but that is okay in our case if we do it, and that is called irreducible. So if we take the boundary conditions into the problem, then it is irreducible, and that means that none of the off-diagonal elements, and that is, if you remember the matrix that I showed you, that they had coefficients b and c. In 1D it would be the b and c coefficients. They are, in my notation, A is diagonal, B is the subdiagonal below, and C is the subdiagonal above. So B is below and C above. So they are indicating the off-diagonals if none of these is 0. So in that case, we can use the Thomas algorithm. Thomas algorithm, that is what you are doing now, or TDMA. That is, I should say, perfect for solving this tridiagonal linear system in this case, that is 1. And we do it then without iteration, that means we do it directly. You give in your matrix, your right-hand side, and out you get directly the answer. That means a direct solution, without any iteration. And what you need there is, you need to do about 8 times the unknowns, number of unknowns, floating point operations. That is important when you want to compare the computational work in the end. So that is something I think one should know, that the TDMA costs about 8 times the number of unknowns of operations. So that is very nice, and now we would also like to do that in 2D. So the 1D problem is thereby solved. what we discussed just before was the pentadiagonal linear system. In 2D. The pentadiagonal linear system that we get for the 2D finite volume method. Is also an example of a banded matrix. Because when we look at it, it will look something like that. A is equal to, and here we have then our diagonal that will contain our AP coefficients. Here we'll have the subdiagonal that will contain the minus AW coefficients. And here we'll have the diagonal containing the minus AE coefficients. So they go all the way through. And a bit away from them, we have the diagonals coming from the minus AS and from the minus A north coefficients. In between we have zeros. So let's see that we close that here on the right properly. So then we have this, and here we have zeros, here we have zeros, and we have also here some zeros in between here. And it turns out if we count, in our case, the diagonals that we have in between here, from the diagonal up to this diagonal coming from the minus A north, or our G, we will find out that we have here Ni. Let's see if I now, I think in our case we would have here actually the Ni plus 2, because we have taken into account also the boundary conditions. So in our case we would have here Ni plus 2. If we did not have the boundary conditions taken into account, it would be Ni. And here we have the same. So that means in our case the bandwidth is Ni plus 2. So we have a banded matrix, and now we could try to solve that also by the, similar to the Thomas algorithm, by LU factorization. However, there we get a problem. So if we want to do that, we will get something, we will get the following thing. We try to express that as a lower triangular matrix, and that will have, so what we want to do now is write this as A equal to L times U. So now I need some space here. And the lower triangular matrix will have ones in the diagonal all the way down to the very end. It will have 0 above because it is a lower triangular matrix. And it will have naturally a subdiagonal that is, because we have also here one. And it will also have naturally something that is coming then from the minus A south, or the F coefficient, something here. So far so good. The problem is that we will get more. When we do the LU decomposition, we will find out that we get more. And let's see. What we will get is so-called filling. We will get also some stuff here. We will get here. So here we will get something. We will get some. So depending on our Ni, we will get here a bunch of additional diagonals. And that is called filling, what we get here. And we get that also for the U matrix. For the U matrix, we will naturally have something in the diagonal, which is not generally 1, something. We will have something above that will be actually the same, I would expect. And we will have something from the minus AN here. And here we will have the same problem. We will get something here, and we will get some additional diagonals here that we have to compute and to store. So this is a matter then of that we lose computing time to compute that, and we also need storage for storing it. So that is G. So what I already mentioned is what we get here is called filling. So this and this here is called filling. And that is a problem because that will lead to more work and more requirement of memory. We can actually analyze the amount of work, that is floating point operations, that we need to do, and we can also count the number of unknowns that we would need. So that means we have already seen what I'm now writing, the solution of the linear system 1 for this A that we have just seen with LU decomposition leads to, and we need a prerequisite for that, A transpose should actually be diagonally dominant. And that leads to what we have seen here, I write again, filling. So that is the problem. And the solution takes, that is the order of the unknowns n, in our case ni plus 2 times nj plus 2, times the bandwidth squared floating point operations. So this is floating point operations. I don't write flops because that is usually floating points per second that we don't want here. And so the memory needed is actually, if you think of it, we need now actually to store all these diagonals. If we had in the beginning here a bandwidth of W, we need W here, we need W here, and we need a diagonal. So we need 2W plus 1 times our number of unknowns n storage places, or arrays to store. So that means we need memory needed is then 2W plus 1 times n arrays. Just to remind you, for the TDMA Thomas algorithm, we just need 3 diagonals. That's it. But the problem is that the computational time gets quite long. And imagine if we go now to 3 dimensions, then our bandwidth will be ni plus 2 times nj plus 2, for example. Essentially ni times nj, so we get even larger bandwidth. And the work gets more and more heavy. And the conclusion is that in 2D, that is what we are discussing here, or even more in 3D, and in 3D, the direct method to solve a linear system. Direct methods are rarely used. So this would be LU decomposition, but in principle would use any method that you can think of. And instead, iterative methods are preferred. So you find some good direct solvers, and if you have, say, smaller problems with not that many unknowns, then it is worthwhile. If you have good direct solvers, small problems in 2D, then you can do it. But of my PhD students, so far only one used direct methods. The others have all been using iterative methods. So then we have to draw our attention now to iterative methods. So, in iterative methods, so that is now the second, so for us the most important method to solve linear systems. Actually, we have not just one, we have many different methods. The point here is we need now a starting vector of the solution. We guess something. In the skeleton program that you got, this guess was 0, just arbitrary. You could do something else. What we assume here that we can decompose or write A as a difference of two matrices, where the M matrix should be non-singular. And then, instead of solving, that is the main idea of solving equation 1, that was AX equal to B, or it would be equivalent to solve if we write, you see A is M minus N, we could also write MX is equal to NX plus B. So I put the N on the right hand side. So it's M minus NX, and I put the NX on the right hand side, then it is equivalent. Instead of that, we solve, when we use iterative methods, we solve the following. That is then the basic form for iterative methods. We solve the matrix M, and now we take the left at the new iteration, k plus 1, and we take the right at the old iteration, k plus b. So now you see how it's working. We distinguish now between the iteration levels. In the beginning, we have here x0. And then we compute a new iteration by solving this system. And the solving mx should be simpler than solving ax. Otherwise, we could do it directly. And this is equivalent, so this is the key point. This is equivalent, but you never should do it like that, because, as I told you before, never compute an inverse unless you are really forced to do it. Solve a linear system instead. But for the mathematical analysis, we need to do that. So when we have this, we get M inverse B. So that is then what this is equivalent to. So, and well, if we have convergence in the end, then the xk plus 1 and the xk, they should be the same. And then when we have convergence, then in the end we should solve the problem that we want to solve. And that is the idea. So we start with an initial guess, and we determine these matrices that represent A in such a way that the M part is taken then as unknown, the new iteration, and the N part is then taken at the old iteration. That gives us then a recipe to do that. Okay, so after the break we'll look at examples, and then you'll see also the method that is implemented in skeleton. That's one of them.